good evening, it's that time again. And instead of just talking purely TOG stuff, we are going to take a very small diversion away onto something tangentially related to the next TOG episode. In fact, we're going to talk about wading and amphibious assault. And I know you might not know why those are connected, all will become clear in the next video. So, moving away from TOG stuff specifically, the reason that I want to talk about wading and amphibious assault is that you need to understand some of the basics of the issues involved in both of those things to understand and appreciate some of the decisions made in the next step in the TOG saga with their amphibious vehicle, because yes, there is an amphibious TOG. So specifically, the question that you need to consider is, how do we get a tank onto an enemy shore? Now, on the face of it, that might appear relatively simple, but the question gets harder and harder to answer with the more knowledge that you have. So let's start by quickly, and I do mean quickly, running through the basic options that we have for crossing water obstacles. Whether in fact we're talking a deep stream, a gully, a river, or in this context, a foreshore protected by the enemy. First of all, you can simply wade through the water. Well, here you are limited to a wading height. This is usually given as the height at which water will enter the first opening in the hull, and you might find this surprisingly low. So, a meter or so, basically 3 foot of wading, doesn't sound like a lot. I mean, we're not even in waist deep water. Yet even this would prove difficult for British vehicles. Now, I'm concentrating on British vehicles because that's what I am particularly interested in. So in 1939, 1940 even, this was still complicated. Water would find its way into absolutely everything, from the final drives to brakes, engine compartment. All of that required sealing, and the deeper you go, the more sealing it would need. So the ideal method, of course, is to simply land your tanks directly onto a beach from a landing craft, assuming, of course, you have some. The second issue is one of flotation. Why do things float? The ancient Greek mathematician Archimedes was the first to consider the flotation issue of any body, and rightly surmised that the buoyancy of a body is equal to the weight of water displaced. In simple terms, a small dense body is not going to displace sufficient water to match or exceed its own mass and thus sink. A larger object will displace more water and thus gain more buoyancy.
The upward force exerted on a solid object immersed in water is equal to the weight of the volume of water displaced by the object. If this force is greater than the weight of the object, that is, if the object possesses less density than the water, the object will float, with more or less of its bulk projecting above the surface. If, on the other hand, the weight of the object is greater than the weight of the water displaced, the object will sink to the bottom. By increasing the volume of the water displaced, however, by building projecting walls on the object and hence increasing the upward force, even the heaviest object may be made to float.
The upthrust from water on a tank is equal to the weight of water displaced. So a 30-ton tank, for example, needs to displace at least 30 tons of water to be buoyant. That's a volume of water, 30 cubic meters. So if I take my 30 cubic meter volume tank weighing 30 tons, it will therefore float. But say a parameter is changed, such as more armor, adding a few tons. The now 35-ton tank, displacing 30 cubic meters of water, 30 tons of water, will now sink, which is not good. So if you want a tank to float, you have to displace more water. How do you do this? Well, you can have an inherently buoyant tank, one which will displace sufficient water to meet or exceed its mass. These are generally, certainly in 1940 terms, rather small, lightly armoured and light. Thus, if you need to float a larger tank, you need to displace more water. And without redesigning your tank, that means adding something to the vehicle to displace more water. The reality is that tanks are not naturally buoyant objects, unless, of course, you go for something inherently amphibious. And amphibious tanks, as said before, tend to be lightly armoured, keeping their weight down so that they float. So there we have it then. The first and most obvious method is flotation. The material of flotation is not particularly relevant, and various options over the years have been considered. You've got K-POC blocks, rubber-filled airbags, and metal pontoons, probably the most common sort. These all contain air or a material substantially less dense than water to displace a disproportionate amount of water and produce a greater upthrust. They do work. They work rather well. And once you get them to work, then the effort is mostly expended in trying to make them streamlined to reduce drag, maybe going for a boat shape. Now, the natural evolution of this is probably taken to its zenith by the Japanese in World War II with the Type 2 car Mi. It's really just a light tank, but rather one with a large hull and designed quite cleverly in such a way that the boat parts of the hull can detach so it can move through the water, and then once it arrives on shore, these can be discarded. The problem, however, is that even working like that car Mi, you end up with a lightly armoured tank, and that's simply not ideal for an amphibious assault, especially against a well-emplaced enemy. If you want a heavier tank, you are therefore going to need substantially more displaced water to create more buoyancy to offset the weight of armour, or think of something else. So there we have the basic of floating a tank. But floating, it's not enough. You've got to move through the water somehow. So you've got propulsion issues. You've also got to hopefully be able to steer your vehicle. So you've got to be able to steer it. And you are subject to the problem of tides, riptides, splashing, overtopping, and of course pesky enemy fire, making this whole method of floating to the shore rather hazardous.
Navigating a tank in a fast-flowing river is more difficult than handling one in the sea. In a river, currents vary at different depths and places, and if, as in this case, the current is flowing at 3 knots and the maximum speed of the DD is 4.24 knots, the tank has small advantage over the current and will soon drift unless she is correctly handled and the necessary allowances are made to enable her to land at a given point. Navigating a waterborne tank is a very different matter from navigating a boat. The rudder of the boat relies for its steering effect on the forward motion of the craft itself. It is a deflector, working by the pressure exerted on its projected area as the craft moves through the water. Without movement of the craft, there can be no steering effect. The steering propeller, on the other hand, is a positive force pushing the tail of the DD, so it acts regardless of whether there's forward movement. If the propeller is set at an angle, it'll push the tail round and the DD tends to pivot on its bow onto the fresh course. This happens whether it's moving forward or not.
The third option for an amphibious tank is really just a version of this increased displacement method. In this case, however, instead of going for fixed floats added onto a vehicle, Or instead of going wider or longer, boatifying your tank, as exemplified by that car Me, you simply add a collapsible screen to the tank instead. This is most famously encapsulated in the DD or Duplex Drive tanks, the invention of Nicholas Straussler, and these are really just an extension of his folding boat designs from before the war. They consist simply of a bracing framework with a waterproof skin made of rubber or waterproof canvas. Added around the tank, these then displace an increasingly large volume of water as the tank enters, to the point where the level of the tank was nearly under the waterline and the remaining volume was air. Air, being substantially less dense than water, creates huge buoyancy and thus the tank would float. Now, that is a great idea, and it does have a few flaws though. First of all, your screen has to be robust enough to deal with the water pressure and wave action. So on the DD tanks, on the Straussler tanks, they have inflatable frames, collapsing frames, and metal reinforcement. It's quite complicated as a system. You also need a bilge pump to make sure that water seeping in or coming in through bullet holes is expelled. And your crew that has an awkward choice to make. They either have to travel half out of the tank for safety, so that in the event that it sinks they can escape, or they could be completely buttoned down for protection from enemy fire, because that canvas screen's not going to stop anything. That, though, means that they then have to travel almost blind behind the screening, as well as considering the unpleasantness of what happens if the vehicle sinks.
The crew of a Sherman DD tank all wear the Amphibious tank escape apparatus in case the tank is sunk. They can then breathe underwater, surface,
The advantage, however, of the system is that it works. It's relatively conventional or normal enough that it doesn't require some great new tank design. It can be added to existing vehicles. Indeed, the first vehicle it was added to was the Valentine, because the shape of it made fitting a screen so much easier. And it doesn't require a large modification or a particularly huge material expense. Canvas is relatively simple as material. The third option is really one of submerged motion. Underwater, you also have a substantial advantage. You're completely immune from enemy fire, right to the point where you're about to emerge from the water, something like the Kraken coming out of the surf to engage the enemy. You would, of course, not be able to fire at the enemy yourself, but then you couldn't do that from a DD vehicle whilst floating either, as the screens covered the front of the barrel, and if you chose to fire in such a way, not only would you remove the waterproofing from your barrel, you'd also remove the front part of the screen and take the aforementioned trip to the seabed. You could, however, fire while doing one of the boatified schemes, or indeed the DD scheme as soon as you get to the shore and drop the screens, but then you could do that with an underwater driving vehicle as well as soon as it comes out of the water and be able to fire. Just like everything else, there is a price to pay. And part of the price to pay is the complications of sealing once more, waterproofing it, and of course the additional problem of navigation, because you can't see where you're going once you deposit it onto the seabed. Now, we're not talking hundreds of meters, maybe 10 meters or so for a small river, let's say 100 meters or so for a foreshore or a big river. Basically go in a straight line, try not to hit any rocks, sort of method. So you can get somewhat around the navigation. Now we shall return to the underwater tank issue for the TOG Amphibian in another episode, but regardless of which of those methods of getting your tank ashore you choose, they all need waterproofing. Although, having said they all need waterproofing, as you see when we come to the TOG one, they figure out a way around that problem, or somewhat around that problem. But basically, regardless of whichever method you need, you're all going to need some type of waterproofing anyway. Okay, so waterproofing. The simple conceit around waterproofing is that bolted tanks leak and welded ones don't. Well, that's not true. We should avoid such overly simplistic explanations, just as critically as we avoid the canard of considering all tanks as just that firepower, mobility, armor triangle. There are way more considerations, particularly in a war. The reality of waterproofing a vehicle is that even welds can leak, and rivets and bolts can be sealed watertight as well. Now, there are extra steps, and the ideal is to have your vehicle sealed during production. High quality welded hulls to ensure water tightness, well fitted hatches with heavy rubber seals, and the all important turret ring seal. Those all work together to keep the water out. All those required that vehicles be used for amphibian work were prepared properly. But again, it's not just as simple as we take a vehicle and we prepare it. The vehicles, as covered in my next book, will show that they needed to be basically new with relatively few miles on the clock. I'll come to why in a second. And if that's not hard enough, then you're going to raise the obvious question of, if my tank is underwater, air and exhaust are the next two questions. So just as you saw with the Tauschpanzer, you might want a raised exhaust to stop water coming in and flooding into the engine. Or you might want a raised flotation for air to be drawn in for the crew or engine as well. With regard to the exhaust, there's no actual reason for the raised exhaust to vent the gas underwater, as it happily gets pushed out at the sorts of depths being considered. I believe it's something like 4.5 meters. Maximum depth for a vehicle like the Leopard 2, for example, so that's plenty deep enough without having to mess around with some complex exhaust system. Now, obviously, the Leopard 2 is not a World War II tank, but even in my research into wading and waterproofing, when they came to consider underwater tank work, there was no need for a raised exhaust. Even driving under the water, the engine was powerful enough to push the exhaust gas out against the water pressure, and the British report even specifically confirms that the myth or concern about a stalled engine sucking water back up the exhaust wasn't founded. They tested it, it didn't happen, so there was just no need for a raised exhaust. So, that's not the only problem with water. You do need some method of getting air to your engine. A raised air intake is the most obvious method. As you'll see when we get to the TOG Amphibian, once more these guys came up with a completely different solution. But we're only talking in basic terms here. I need to set the knowledge so that when you come to think about the TOG Amphibian, you know why decisions were made the way they were. But air is only an issue, exhaust is only an issue. Regardless of what you do, as soon as your tank gets wet, you now have to consider corrosion. So salt water in engines, especially electrical fittings in engines, do not make good bedfellows. They do not like each other, they do not work well together, and the corrosion on metals is terrible. Even after you come out of the water, even if you dry it off, you still get corrosion on the surface because of the electrolytic effect. So it substantially reduces the lifespan of vehicles to the point where the British estimated that the life expectancy of a combat vehicle was basically halved by a single seawater wade. So if you are expecting your Cromwell to maybe last 2,000 miles, if you decide to do a sea wade with it, you can now expect its lifespan to just be 1,000 miles in simple terms. that's really not good. So let's try and avoid getting our tanks wet. Further, just as I said before, waterproofing your existing vehicles is only part of the process. It's surprisingly difficult. The British were quite clear from extensive testing that you should only use new vehicles where possible. The wear and tear driving on a road or off-road would cause buckling, stress fractures, weaknesses in the seams and seals due to wear. There'd be mechanical damage from things like tree stumps, rocks, or even just gravel. And the kits made to fit vehicles, so some of that weld wear and some of the ducting, had to be so carefully made and fitted that even a small difference could mean failure because the water will find its way in. In terms of pre-waterproofing mileage for A vehicles, a tank like the Churchill was specifically not to be used for wading if it had more than 400 miles on the clock. Wheeled combat vehicles, 2,000 miles on the clock. Things like trucks, when we get to consider how difficult it is to waterproof a truck with an open chassis underneath, 500 miles. So if you are preparing for a massive amphibious assault like something like D-Day, you need to mass up a lot of new vehicles and spend a lot of time and effort waterproofing them. You can't just use your old tanks. So that's that. You have a massive problem in not only getting tanks, but tank-like vehicles or trucks ashore. The more electronics involved, the more problematic it is. Unless you incorporate waterproofing and wading into the design from the outset of your vehicle, the amount of work required to fix that issue later on is simply enormous and very restrictive in what options you have. Water, particularly salt water, is very damaging for vehicles. And if you're planning on an amphibious armoured vehicle for assault, you really only get to choose 3 options, of which only 2 are reliable. The first, as mentioned, is the waterproofing or Duplex Drive, that Strauslerization of your tank. This was still a method used post-war for tanks. You will famously see pictures of Centurion and even the Swedish S-tank using this system. It has, however, fallen increasingly out of favour. The second option is, just as I mentioned before, the Leopard 2, this driving underwater option. With modern production, it's much easier to make sure that your welds do not leak, that you have those heavy rubber seals and the all-important turret ring seal. And the vehicle doesn't then need these giant floats that have to be hauled around by support vehicles to do that surface flotation. It can drive underwater using a raised tube for air intake. And the third option is make your tanks totally dedicated to amphibianness. The US LVTP-7 type vehicle and later attempts at advanced amphibious concepts really show that the vehicle that's perfect for getting from the ship to the shore is not ideal on shore. So there really isn't a great solution in that amphibious light tank. You are still limited by the basics of buoyancy, weight, and armor. So having covered all of that basic information, that will be the basis on which you'll be able to go forward from here to the next video on the TOG amphibian and understand why things were done the way they were, without having to fill that video up with the background data on how wading and waterproofing and all that business works. So that's it for now. Thank you very much for your time. If you like this video or the others, then please like, share and subscribe. Please feel free to follow me on FWD Publishing on Facebook or WordPress or my Amazon author page. And if you want to support my work, my research and further books, then please consider supporting me via Patreon. Links are in the chat below. Thank you very much.